Good morning one and all. Now we are going to see the topic called cache coherence. Before going into the issue of the cache coherence problem, now we are going to see the basics of the memory hierarchy and some basics of the cache so that we can be familiar with the cache coherence problem. First one is memory hierarchy. Memory hierarchy is nothing but is a structure that has a different level of memories as a distance increase from the processor. That is, initially the memory hierarchy starts with registers, followed by cache, then followed by main memory, then secondary memory, then auxiliary memory. So the CPU register is the only thing that is actually present inside the processor itself, whereas other thing called cache, main memory and secondary memory, auxiliary memory will reside outside the processor. So now they are organized in a such way that they increase in this speed, that is time taken to access the data in the registers will be high compared to that of the cache. Time taken to access the data in the cache will be faster compared to that of the main memory. Time taken to access the data from the main memory will be faster compared to that of the secondary memory. It goes on. And they are organized in a such way that there is increase in size or decrease in size. Increase in size, that is CPU registers will be smaller compared to that of the cache. Cache can hold a small amount of data compared to that of the main memory, and main memory can hold a small amount of data compared to that of the secondary memory, and it will be goes like this. The cost of the CPU registers will be costlier compared to that of the cache, and cost of the cache will be costlier compared to that of the main memory, and the cost of the main memory will be costlier compared to that of the secondary memory. So this is how the memory hierarchy is get organized. So when you want the data to be accessed, the processor have to spend most of its time in waiting the data to be accessed from the main memory. So the performance of the processor will be degraded. To overcome this problem, we need a solution. So the solution is nothing but the solution is addressed by cache. So cache will make the main memory appear to be faster to the processor. Even though the main memory is not faster, the cache will make can make to appear the main memory faster to the processor. So this is the processor, and this is the cache, and this is the main memory. So the cache will make the main memory appear to be faster to the processor. This is what the role of the cache. So whatever data when you search in the cache, if it is not available in the cache, it have to be bring from the main memory to the cache. This is how the actual data transfer happens between the main memory and the cache. The main basic principle on which the cache works is principle of locality. What is principle of locality of reference? They are categorized into two types. One is temporal locality of reference. Second one is spatial locality of reference. What is temporal locality of reference is, if an instruction is executed recently, there is a high chance of executing the same instruction in a near future. That is called as temporal locality of reference. For example, I am studying a book called Data Structures from the library, and I have bought that book from the library to my desk, and I am referring it now. There is a high chance of referring the same book again after some time. That is called as temporal locality of reference. Second one is spatial locality of reference. Spatial locality of reference is nothing but the instructions that has the close proximity with the instruction that is recently executed will have a high chance of executed in the near future. Suppose in the library I have referred a book called Data Structure written by one author A, and there is high chance of accessing the other books on data structures by author B. So I have to bring up all the books that is related to data structure on my desk, so that if I access the book A now, there is high chance of using the book B in some time. So that is called a spatial locality of reference. So this two was the working principles of cache, by which the data is transferred from the main memory to the cache. And the desk is nothing but the library, desk is nothing but the cache, and the library is nothing but the main memory. So whenever I need of data, I have to bring the data from the main memory to the cache and use. The bringing of data from the main memory to the cache works based on the two principles. One is temporal locality of reference and another one is spatial locality of reference. And apart from that, I told you that a processor is need of some data from the main memory. This is cache and this is processor. Suppose I need a data called X to be used by my processor. If it is actually not present in my cache, what I have to do is I have to fetch the data X from the main memory. This is how we think, but what actually happens is, if I am needing of some data X which is not actually present in the cache, then that is a cache miss. So I have to bring the data X from the main memory. But we will not always bring one particular data called X from the main memory. We will always transfer the cache line containing the X from the main memory. What is cache line? Cache line is nothing but a block of data in the memory. That is, whenever you need some data, you will not bring the same single data from the main memory to the cache. You always bring the data as containing in the entire cache line will be brought to the main memory. So the cache line containing the X, that is cache blocks containing the X, will be brought from main memory to the cache. This is how the data transfer happens between the main memory and the cache. So there will be always the block transfer between the cache and main memory. So when I need X is the value that is actually needed by the processor, then there will be a word transfer between the cache and processor. That is, when I need X, the entire block or cache line containing the X will be transferred from the main memory to the cache. Later, when that particular X alone will be transferred to the processor. So the transfer between the processor and the cache is called as word transfer, whereas transfer between the cache and the main memory is the block transfer. So this is how it happens. I told you that there is a cache line. Whenever a data is brought from the main memory to the cache, it will be brought in the form of a block. So that cache block is of size. Sometimes it will be 64 bytes. Sometimes it will be 28 bytes. So the size of the cache line is depending upon the processor that we use. It varies from one processor to another processor. So this is how the cache actually works. Now we are going to see the problem of cache coherence in detail. Before going into the cache coherence problem, we have to be aware of the two main architectures that is available in the multi-core. That is, one is shared memory architecture and another one is distributed memory architecture. So shared memory architecture, we will be having a number of CPUs or cores that have to access this common memory via interconnect. Interconnect is nothing but a collection of wire or buses through which the CPUs will access the common portion of the memory, that is shared memory. Here I have the CPU 1, CPU 2 and CPU 3. So these are the three CPUs available. They are sharing the common memory. When they need a data in the common memory, they have to access via the interconnect. Interconnect may be a bus or a switched interconnect or crash bus or omega network. There are a lot of interconnect networks available, but we are very well familiar with a bus. Bus is nothing but a collection of parallel wires. So whenever a CPU 1, 2, 3 is in need of data, they have to collect the data from the memory portions by means of an interconnect. This is how the shared memory architecture works. And next type of architecture is a distributed memory architecture. So here we will have a number of cores. Each core will have their own private cache available. This is core 0. The core 0 is having a cache 0, and we have another core called 1, and that core will be having a cache 1, and I have another core called core 2 that will be having a separate cache 2. So every cores or CPU will have their own private cache and memory. They have their own memory. So the interconnect is used to establish a communication between these processors. So when the processor want to communicate with the other memory portion of the other core, they will communicate via interconnect. So they have their own portion of memory. So here if there is any communication between the processor, that does happen with the help of the interconnect, whereas in the shared memory architecture, with the help of the interconnect, we will access the common shared memory portion. In the distributed memory, the CPU or cores can interact with each other, communicate with each other with the help of the interconnect. In the distributed memory architecture, every core will have their own portion of a private memory and a cache. This was the architecture of the distributed memory, and now we are going into the actual problem of cache coherence. And how we are going to address that particular problem. We are going to exploit what the cache coherence problem is, and how we are going to overcome that problem with the help of some techniques called snooping or directory based coherence. First one is cache coherence. To understand the issue or a problem of the cache coherence, I have to be aware of one particular program. I am taking an example, that is shared memory program, how it works and how the cache coherence problem occurs. For that, I have taken the shared memory program. In my shared memory program, there are two cores. One is core 0 and another is core 1. Two cores. Each cores have their own private cache. This is cache of core 0 and this is cache of core 1. This is the two cores, they have their own private cache. Now, there is a common memory because we have taken a shared memory program as an example. They share a common shared memory, and there will be an interconnect. With the help of the interconnect, the interaction between the processor and the memory and the data transfer between the memory and the processor will actually take place. This is my shared memory program. My program consists of two lines. At time 0, the core 0 will be executing a statement called x naught is equal to x. At time 1, it will be executing a statement called x is equal to 7. At time 2, it will be executing a statement that is not involving the x. In the core 1 at time, it will be executing x is equal to 2 into x, and it will at time 1 it will be executing a statement that is not involving x. At time 2, it will be executing a statement such way that z is equal to 4 into x. Initially, I am taking time 0. At time 0, what happens? The core 1 will be executing a statement called x naught is equal to x, and core 1 will be executing a statement called y is equal to 2 into x. What I am going to say is, this is the core. Every core have their own private cache, but there will not be any problem until they read the shared data. when they try to write or update the shared data, the problem arises. Even though these two cores have their own private cache, if they have some shared data, if they are reading that particular shared data, there will not be any problem. If they try to write that particular shared data, then the problem arises. For example, these two cores 0 and core 1 is using the common shared data called X. That is initially 2 in my main memory, and one of the core is trying to write the value to that particular X, so that the further value usage of X will result in the incorrect value. So whenever two cores are sharing some data, there will not be any problem until they read to that particular shared data. There arises a problem when they try to write that particular shared data. Here X is the shared data between the two cores, whereas each core is having their private data called X0, and this is the private data X0, and this is having a private data called Y and Z. These are the private data, but both the cores are sharing the common data called X. So first, initially at time 0, I am assigning X0 is equal to X. That is, I am assigning the value of X to my X0, which is my private variable. So the core will be searching the cache for finding the value called X. The X will not be actually not available in my cache, so it have to fetch it from the main memory. I have already told that whenever there is a data transfer between the main memory and the cache, it will be in the form of a cache line or a cache block. So the block that contains the entire X will be copied here to the cache. So the X is copied from the main memory to my cache. Now at time 0, the Y is calculated in core 1, that is Y is equal to 2 into X. So the Y value is actually not available in the cache 1. So the core 1 will try to fetch the data from the main memory and load it to the cache, so that here X value 2 will be copied to my cache. So the Y is calculated 2 into 2, that is Y value will be 4. And at time 1, the core 0 will be executing a statement called X is equal to 7. That is, it is writing to the particular shared data. I have already mentioned many times, write to a shared data will always end in some problem or inconsistency. So when they try to write to the value 7 to the X, it will search the value for the X in the cache. It is available. So it will change the value 7 instead in the cache 0, but it is not actually updated to the main memory. So first the X value is updated to 7, then I will have some statement that is executed by core 1 without X. I have some statements like anything that involve without involvement of X, and at time 2 the core 0 is executing the statement that is not involving the X, that we don't bother. Now in the core 1 at time 2 I am executing a statement called Z is equal to 4 into X. So what happened, I need a X value to find the Z value. So I will search in my cache. The X is actually available, that is 2. But I have already updated the value of X in the core 0's cache, but that is actually not unaware to the core 1's cache. So it will be using the old value and it will calculate the value of Z as 4 into 2, that is 8, but it is no wrong value. Either it should be a 28. But due to the updation of a shared data in a private cache, the updation is not known to the private cache of the another code. That sends in the problem called cache coherence problem. That is, even though the value updated in a private cache, it is even reflected to the main memory, it is not known to the cache of the core 1, because they have already cached the data X in the starting or time 0. They will be using their same own data. They will know the new data until they have evicted or reloaded the X from the cache. So even though there are two policies have to be followed for maintaining the consistency between the cache and the memory, because I am bringing a block of data from the main memory to the cache. For maintaining the consistency between the cache and the main memory, I follow the two methods. One is write back and another one is write through. The processor will be following any two of these techniques for making the data consistent between the cache and the main memory. If suppose I am following a write back, what happens? When I try to edit this X or unload the X from my cache, at that time I will update the value to the main memory. Write back is nothing but when I am editing the X from the cache, I am in need of new data that will be loaded from the main memory. So there is no space. I have to edit my X from the cache. So at that time the updated 7 will be made consistent with the main memory. So here I will, at that time I will change that the value of X is 7. But the second is write through. Write through technique is nothing but whenever I update the cache, I will also update the main memory. They will be always consistent. When I write to a value in the cache, it will also be reflected to the main memory at the same time. That is called as write through protocol. Even though I use this write back or write through, the data in the cache will be old value. They will be using that same old value, either of using this technique or this technique. If you can use this or this, that is not a problem. The cache coherence problem will occur because they are already cached the value of X and they will be working on that old value. So this is the cache coherence problem. To overcome this cache coherence problem, I have two more techniques to address this cache coherence problem. One is snooping based coherence. Another one is directory based coherence. First is snooping based cache coherences. Here this technique is used to address the cache coherence problem because the value updated in a private cache of core 0 is not known to the cache core 1, and due to that it is already cached the value of X and it will be making use of that old value and the results will be incorrect. To overcome this cache coherence problem, I have to go for two more techniques, snooping and directory. Snooping based protocol technique is nothing but here is a bus based system. Here we will have a number of processes or a cores connected to a common bus. So I will have a number of cores. They will be connected to a common bus here, that is interconnect. Interconnect may not be always a bus, it can be any things like switch interconnect or anything. So number of cores connected to the bus. Suppose I have a cache in my core 0, that is cache 0. I have a cache in core 1, that is cache 1, and they both share common data called X. What happens when I try to write the value to the X? I will broadcast a message that I have updated the value of X. That message is broadcasted in the interconnect, so that all the cores that are connected to that interconnect can see that message that have been broadcasted and they can invalidate the value of X. Because the cache 1 is having the X and initially that will be a 2. Now the cache 0, core 0 have updated the value of X as 7, that is updated in cache 0. That message will be broadcasted in the interconnect. That broadcasted message will be seen by core 1, and once they have seen that particular message, what they will do is they will invalidate the value of X. That is, they will invalidate whatever value you have in your own private cache is not up to date, so it will invalidate. This is the one type of method for maintaining that coherence between the caches of a multi-core. So whenever I write to a data, I will broadcast that particular message in the bus. So whatever cores it is connected to the bus will be seeing that particular message. If it is having the own copy of X, it will be invalidating that particular value of X. So whenever the cores need a value of X, it have to be fetched from the main memory. This is the one way of achieving a cache coherence between the multi-cores. And I have some disadvantages in snooping method because it is first one is drawbacks of snooping is it is expensive. if it is not scalable for a large network, when I am doing it for a course that have more than 8 or 9, it will actually degrade your performance. So it is not scalable for larger networks. And third one is, due to the broadcast of the message in the interconnect, what happens? It will actually degrade the performance. The interconnect is mainly used to access the data from the memory to the processor, but the role of the interconnect is changed here. Here they will be broadcasting some messages. The broadcasting of messages in the interconnect actually degrade your own performance. So the time taken to access the local memory will be more. So that way the weighting of the processor will increase. That will actually degrade your performance. So what is the third drawback of snooping is, it will degrade your performance, and because the time taken to access the local memory will be high, because due to the sending of these messages, the actual data fetching will be delayed. So the time taken to fetch the data from the local memory will be high. That will actually degrade your performance. These are the drawbacks of snooping based protocol, and to overcome these drawbacks, I have to move it for a directory based coherence. And next, second method to achieve the cache coherence is directory based coherence. Directory based coherence is, due to the broadcasting of messages in the interconnect degrade our performance, and it is expensive and it is not scalable for the large networks. These are the drawbacks made us to go for a next type of an approach called directory based coherence approach. In this approach, I will have a directory. So directory here is the data structure. So this data structure is distributed among all the cores. It is distributed among all the cores. So what happens is, a directory is maintained for each cache line. Suppose if I am fetching the data from the main memory to the cache, for the entire cache line I will be maintaining the directory, and this directory is updated whenever I write the value. So holding the value, when I try to write the value to that particular class, the directory will be updated, and that particular directory will be consulted. What are the cores that are holding that particular value will be invalidated. I will explain you with an example. So directory is a data structure. That is, initially the first bit of the directory is called as dirty bit. That is, dirty bit is it is pointing to a memory location. This memory referencing the memory block. So whenever I write to that memory block, this dirty bit will be set to 1. If there is no write, I am just reading, the dirty bit will be always 0. And the directory will first contain a dirty bit that says that if it is a 1, every dirty bit is referencing dirty bit of a directory. Suppose I have a cache line called B. For the cache line B, I am maintaining a directory. So what happened? The first bit will be a dirty bit, this pointing to the B. If there is any write or update to the block B, then this bit will be set as 1, or else if I read the block, then that is not a problem, it will be set as a 0. When I try to modify that particular memory block, it will be set to 1. And the remaining fields of the directory is, if I have 4 cores, I have to be maintaining 4 fields. Each field is pointing 1 core. If it is core 0 and core 1, core 2 and core 3. So directory is consisting of some field. First field is called as dirty bit, that is pointing to a memory block. Whenever a write is happening in that particular memory block, the dirty bit will be set to 1, otherwise it will be a 0. Whereas the remaining fields depends upon the number of cores. If I have a 5 cores, we will be having a 5 field, and if I have 4 cores, I will be having a 4 cores. So now I will explain with an example. Here I have 2 caches in each core, core 0 and core 1. I have 2 caches, and this is the directory. I have told that the directory is maintained for each cache line or a cache block. So for a cache block called B, I am maintaining a directory called B. So the first bit is the dirty bit, as you all very well know, and the remaining bits is the number of cores. Here I have only 2 cores, so I will have only 2 fields. This is for core 0 and this is for core 1. So this is the actual directory of my block B. Now the first, the core 0 and core 1. There are 2 cores. The core 0 is requesting the read for B. What happens? The directory for the B will be consulted. Here there is, every core is not having any field. That means no data is holding by, no data, no block, no cache is having the block B. So it have to be fetched from the main memory. So I have to fetch from the main memory and I have to send it back to my cache. So once I am sending back, what happens? There are 3 states. One is shared state. Second one is invalidate state, and third one is exclusive state. That is, shared state is nothing but, this is are the states that is maintained in the cache. So shared state is nothing but at least one processor is having the value cached, has the data cached. That is, one process have the block B in their cache. Invalidate is no data, no processor is having the data cached. And the final one is exclusive, that is only one processor is having the data cached. So that is, only one processor is having the data cache. Shared is at least one processor is having the data cache. Invalidate is no processor is having the data cache. So initially no other block is having the data cache. Now I am going to copy it to the core 0. So I will copy in the state called E, that is only one processor is having the data block B and it is not updated. Main memory is not updated. Main memory is not up to date, but I have copied the data. Only one processor, that is core 0, is having the block B. So it is in the state of exclusive. So I am copying exclusive. I am copying the block B to my cache. Now the cache 0, that of core 0 is having the block B. So I have to make it as 1 because the core 0 is now having the block B, and the dirty bit is, it is not going to write because it has sent the read request. So the dirty bit will be a 0. This what happens when the read request is came from the core 0 for the block B. So what happened? Now the core 1's cache is requesting a write request for B. What happens? It will check the directory. Whatever operation read or write, I have to consult the directory and take the necessary action so that I can maintain the consistency between the core's cache. So when I ask for write B, what happens? The directory for B will be referred. So it will check that core 0 is now having the value of block, otherwise core 1 is 0 now, and the dirty bit is 0. So there is read only made to the block B, write have not been done. So what happened when they request for the write, this dirty bit will be set to 1 and invalidate message will be sent to, because core 0 is 1, that means the core 0 is now holding the block B. So the invalidate message will be sent to B so that the block will not be invalidated, back will be invalidated, so that we cannot further use the B from the cache 0. So that is now made 0 because I have invalidated that. Now the core 1 will be holding the block B for write. So I have to here make it as, because I am going to modify, I have to mention the state called modify, and the cache 1 will be, B will be placed in the cache 1. So whenever I have to write to a particular value of a cache, what I have to do is I have to refer that cache line directory, and if any of the cores that is having the value 1 should be invalidated, then I have to copy that particular block to my cache and I have to update, so that here the block B is updated, invalidated. So what happened? They cannot further use that. Whenever they need the block, they have to fetch it from the main memory. This is what I can make the consistent between a cache. And this is also having some drawbacks because I have to maintain a directory for all the cache lines. So the storage is the problem because I have to maintain a separate data structures for a directory. And another problem is, that is not a problem, that is advantage. The another advantage is here the core that is containing the current core that is containing the cache alone contacted and said that the cache is invalidated. We are not disturbing the other cores that is actually having the not having the value of block B. So the core that is containing the B alone will be contacted, whereas in the snooping protocol we have to contact all the processors. We are just broadcasting the message in the interconnect so that all the cores that are connected to the interconnect will be seen. So all the caches, cores caches have to be contacted. Here the core that is containing the only the block B can be get contacted. This is the advantage of the directory based approach. And for final topic is false sharing. The false sharing is mainly to tell us this, nothing but caches are always operate on blocks, not on the individual variables. Not on blocks, that's not individual variables. That is, I have told that whenever you need a data from the main memory, you have to copy as an entire block from the main memory to the cache. So to explain that example, I have some coding like, initially I have a program int I m and double y of m for I is equal to 1, I less than m, I plus plus, I have to add the value. So initially I have a cache block containing 8 double values, 1, 2, 3, 4, 5, 6, 7, 8. So this is y of 0, this is y of 7. I have a cache block. So this cache block is of double value. Double means you already know that double is of 8 bytes. So now this is my serial code that is run by one particular code. I have to parallelize this serial code because there are two cores here. So I have to equally divide the work among the two cores. So I have to parallelize. For parallelizing, I am dividing now the m value, m is equal to 8. I have 8 values. What the program is saying that I have 8 double values. I have to fetch each double value and add it 1 to that particular double value and store it back to the same location. This is what my program works. So for 8 location, here m is 8. For 8 location, I have to fetch the data, add by 1 and I have to store it back. So this is what my serial code works. I have to parallelize this code for 2 cores. So I have to equally divide the iterations between the 2 cores. For the iteration here I have 8 locations. So first 4 locations should be operated by core 0 and remaining 4 locations should be operated by core 1. This is the parallelization of the code between the 2 cores. For that I am doing some changes in the code such way that I am core count and iteration count. So these are the variables, and double, as you know that we are going to fetch one double value and we have to add it by 1 and store it back. So I have to parallelize the code between 2 cores, that is core 0 and core 1. The core 0 will be executing for I is equal to 0, I less than iteration count. So what is iteration count is? Iteration count is nothing but the total value. Here we have 8 values to be fetched and we have to add it by 1 and store it back divided by core count. Here we have 2 cores, that is 8 by 2. The iteration count will have the value of 4. So for 0 to 3, this is 0, 1, 2, 3. The addition is done by core 0. The remaining 4, 5, 6, 7, it should be done by core 1. So for this I plus plus, I have to fetch the value of y and I have to add it by 1 and store it back. For remaining half, for I is equal to iteration count, I is less than or equal to iteration count into 2i plus plus. For remaining portion, that is for from 4, 5, 6, 7, this core will be fetching the data, double data, add it by 1 and store it back. So y of I is plus is equal to 1. So here I have 8 double values, y of 0 to y of 7. I have to fetch each of the y of 0 8 double value and I have to add it by 1 and store it back. This is what how I need. So this is the double 8 double value and my m is 8 because I have mentioned m as 8. It is 8 double value. I am going to fetch one double data from each cache. So and I will be adding and I will be storing that. So this is what my operation works. Here what I am going to do is I have splitted the serialization program into 2 programs so that it is executed parallelly between 2 cores, core 0 and core 1. And now what happens is the cache line, I told you already in the beginning of the lecture that the cache line size will be depending upon the processor. Here the cache line size is 64. Whenever you need a data, the entire cache block will be copied to the main memory, not the single data. So here I need a first initially y0, y1, y2, y3 will be processed by core 0, y4, y5, y6, y7 will be processed by core 1. This y of 0 is the value that is first executed by this core 1 because this 3 values is core 0 and this is core 1. The first y of 0 is processed by core 0. It will fetch the data. It will try to search the data in the cache. It will not be actually available in the cache. So the entire block containing the y of 0 will be brought into the main memory. So what happened in the core 0's cache, I will be bringing the entire cache line. So what happens? Y of 0, y of 1, 2, 3, 4, 5, 6, 7 will be brought to my core 0. Even though my core 0 is going to operate only on y of 0, 1, 2, 3, but my concept of bringing the block from the main memory will all be in the form of a cache line, entire cache line. I have got all the data. But when this core 0 is adding 1 to the already existing content of y of 0, what happens? It will be adding and storing the result. When I store the result, I am writing to the cache line. So I have to invalidate the copy of the cache line containing in the other cores. So what automatically happens? This core 1 will be also bringing the entire cache line for the addition of 4, 5, 6, 7. But due to this write, I will have to invalidate because I have made a write to that core cache line. What happens? It should be invalidating the all other cache line in the other copies of a core. So I will be invalidating the entire cache here also. So whenever they need a data for y of 4, 5, 6, 7, they have to fetch it from the main memory. Rather than they are not using this portion, core 0 is invalidating because it is writing to the y of 0, y of 1, y of 2, y of 3. But this is making use of 4, 5, 6, 7. Even though they are using the different set of data, this will be invalidating this because the entire cache line is copied to the cache. So every time when they need y of 4, 5, 6, 7, they have to fetch from the main memory. So this is the problem. This problem is called as false sharing. The false sharing will not result in a wrong result, but it will always degrade the performance because even though we have a value undisturbed in our cache line in core 1 for y of 4, y of 5, y of 6, y of 7, we have to always fetch the data from the main memory because write to the cache line in core 0 have invalidated the cache line in core 1. So what happened? This write made the invalidation in this core. So what happened? They have to fetch the data always from the main memory. Right.